So with an AC circuit, next question we want to ask is, what about power in the AC circuit? Because we talked about DC circuits, and DC circuits are pretty straightforward. With a DC circuit, we have a load resistor, we got a power supply, and so we have current that flows right here. We know that the power supplied is I times V. The power dissipated equals I squared R. And so this is pretty straightforward. We've already derived all that before. So now the question, what about a circuit that is an AC circuit? Simplest AC circuit. Got a resistor, got a voltage. The voltage is now some V0 sine omega t. But once again, we're going to say that the power is going to be I squared R, because that's really the only place the power is being dissipated is in the resistor. But the problem with that is that I keeps changing, and so the power keeps changing. So we want to know what's the average power dissipated. And this is where we would say that the average power dissipated, so this is the P average, is going to be equal to the I RMS squared times R. Now, if you remember, that makes sense because of how we defined RMS, which is like the time average of this. So, in fact, RMS squared would be, remember, RMS is the root mean square of this, so root mean square. So you square that, and in fact, I RMS squared is quite literally the average of the square current. And so, so that would give you the power dissipated over time. So that'd be the average power. You don't necessarily need to know the instantaneous power. You have 60 hertz in your house. You'd have something that's turned on, like an incandescent bulb or a heater or something. You're not interested in how much power is dissipated every thousandth of a second. You want to know what the power is on average. Okay, so this is how you do it. But what about a little bit more complicated system? So we now have an RLC. So we have an RLC circuit. And so the voltage is still some V0 sine omega t. But now we realize that the current through here is going to be something different. The current is actually out of phase with that. Remember our phasor diagram. If we draw a phasor diagram here, then we've got the voltage and then we got the current that's out of phase. So the current is actually going to be equal to some I0 sine omega t plus a phase factor. And so the current is now going to be out of phase with it. And so we say, well, how does that affect what's going on here? And so we look at it and we say, well, if we imagine, we got the voltage, we got the current, again, let's consider the voltage. We have the total voltage is not going to be in sync with the voltage necessarily on each element. Everything's out of phase with each other. The current's not going to be necessarily in sync. Phasor diagram, once again. So we have the phasor diagram, okay. For a series circuit, everything has the same current. So we have the voltage on the resistor, we have the voltage on the inductor, we have the voltage on the capacitor. Okay. And so the voltage on the capacitor and voltage on the inductor are all out of phase with each other. Okay. And then the total voltage after we do all the vector addition is like that. So there's a phase right here. Okay. So there's our phase angle. Okay. Well, in our series circuit, the only thing that really matters is what's going on with the resistor. The capacitor and the inductor do not dissipate current, they just temporarily store it, and it goes back and forth between the two. It's the resistor that's dissipating. So once again, we would say that the power dissipated, the average power, is going to be equal to IRMS squared times R. Well, if you remember before, we had said that the current times the voltage is the power supplied. Well, that's not necessarily the case here, because the only part that matters is the part that is in the same direction. So the component of the voltage that is parallel to the current. So the power supplied, instead of being just I times V, is going to be I times V times cosine of the phase factor. Okay, and so that's going to be really what we have here, and it's not and it's not just that, it's going to be the RMS values of that. So again, we're not interested in the instantaneous values. So that's going to be the power supply. So IV cosine phi. So for example, you've had an electric motor, it has a certain inductance to it, a certain resistance to it, and it's got a current load in it, and it's got a voltage, but you don't just multiply current times voltage to get the power. So it's a little bit more complicated than that, and I'll do some examples in just a little bit. Another example where power comes in is a transformer. So if we have a transformer, we have an AC signal right here. Okay, transformer, and the symbol for a transformer is this, basically two coils here. So this is coil, this is the primary coil, that's the secondary coil right here. So we would say that we've got current flowing in here, we got current that's flowing over here. So naively, we would simply say that we could just imagine that the current and voltage are the same phase shift from each one, so we don't have to worry about the power factor necessarily. And so we could then say that the average power in equals the average power out. So the average power in, so power in equals the power out. Okay. And so that means that the I in V in equals the I out V out. Or if we use our notation of primary and secondary, the I primary voltage primary equals the I secondary voltage secondary. And so what would happen is that your capacitor would either step up or step down the voltage. We talked about that in lab. So it would either step up or step down the voltage, and the current would likewise change. So IPVP equals ISVS, so that means IP over IS equals VS over VP. So there's an inverse relationship here. So you might have a transformer that has high voltage, low current. So in other words, a charger for your phone or your computer. So it would plug into the wall here, okay, then transformer. And so what would happen is this is 120 volts, okay, coming out. Just to make the math easy, let's just say 12 volts coming out, 12 volts at 2 amps. Well, going into it has to be the same current times voltage. So you know, this right here, I times V is 24, so I times V equals 24 over here. And so so what does that mean? Well, that means that over here, the current has to be 0.2 amps. So that means you might have 12 volts, 2 amps out, but you got 120 volts, 0.2 amps in. And so step down transformer steps up the current. a step up transformer would step down the current. And we've done an example of that, basic concept of that way back when, before spring break. So these are some of the basic ideas right here. And again, the voltage is directly dependent on the flux in there. And so so we know that the voltage in the primary is the voltage in the secondary, what the number of turns in the primary is to the number of turns in the secondary, which is also related to the current in the secondary divided by the current in the primary. So these are your relationships here for the relationship between the voltage and the current and the number of turns in there. So that's your transformer relationships right there. So with that, you can actually figure out all the stuff that transformers do. And so that has an interesting sort of thing too, because that means that you could then talk about the impedance of the circuits as well, and how that relates, because that also relates to the secondary and the primary currents. So, but we'll talk about that later.